CatBoost section. I'm here in my CatBoost section, and you can see that I've set this up so that I can optimize the hyperparameters. The first thing that you do when you're using this Bayesian optimization library is you want to use, you're creating a function. So it's def and it's called CatBoost opt, and these are the hyperparameters that I'm doing. And what you want to do generally is use the names the way that they actually appear um, for the actual, the way that they're supposed to be written for the actual function. So n estimators, max depth, learning rate, max bin, subsample, num leaves, L2 leaf reg, model size reg, and bagging temperature. So in common with most trees, CatBoost has the number of estimators or trees is important. The learning rate's important because it's a gradient-based thing. Subsample, which means, like subsample of the data set that it uses. It doesn't train necessarily on every point. L2, leaf reg, num leaves, depth, these all control the amount of overfitting. And so, I want a model that's expressive, but I don't want it to overfit. So these things will help with that. Max depth is something that most trees have, like random forest and XGBoost. They all have a depth thing and leaf thing, but um, I'm not sure if random forest has number of leaves. But then Grow policy loss guide is sort of unique to CatBoost, but I mean I wouldn't really worry about it. I was using it because I wanted to use best model, but I don't want to do this anymore. So this is sort of just it's kind of a default value I think anyway, so it really doesn't matter that I've written it. And bin again is like how many samples you want to put into a bin. Because like many of these things, they'll tend to bin the data so that it can make it the choice of like how to make a split, basically. Model size, reg, and bagging temperature, these are all things that, again, sort of help with, these are sort of forms of regularization and just sort of, making sure that the model is not too complicated and that it has some good generalizing power. So again, what do I want out of this classifier? Well, I want it to do well on a cross-validated test. So basically, I'm using CV is RSKF, which is my repeated SKF stratified k-fold, and it's the same one. So it should basically be the same, like, what was it, 10 sort of partitions of the data, and my scoring is still the Matthews, and I'm still running it over the entire data set. So here are the ranges for the CatBoost hyperparameters. Some of this is just guessing, some of this is just experience and sort of trial and error. But for example, with depth, depending on different situations, I very rarely end up just using 2 or 3 because that's usually pretty simple. For complicated data, you often need 4 or 5, and in this case, you may want to go up to like 15 or something like that. Even though at that point it's kind of, there's a really big chance that you're sort of overfitting at that point. But, just if you just want to see what happens, you can. Learning rate again between 0.01, usually 0.5. You don't do really low learning rates like you would with deep learning, where it could be like 1.00001. This one usually is like kind of in the 0.1 to 0.5 range. And these are also just sort of general rules of thumb types of ranges for these things. And, again, if one of these is suboptimal, it can throw off the entire result. So that's what's dangerous about having so many hyperparameters. Again, if worse comes to worse, you just start with a major 3 or even 1, which I guess would be n estimators or learning rate. But n estimators, depth, learning rates, subsamples, like I would be comfortable with doing 3 or 4 and thinking that, I've done enough, so to speak, to sort of optimize it. But let's run this and see what happens. So I'm going to run this, sorry, it's 2 points, initial points, and 20 iterations of this Bayesian optimization algorithm. So, we're starting out with 0.9218. So far that's the best value. And now you can see by the virtue of the fact that this is pink that we now have a new champ. The new highest value is 93.56, and it's these are some of the values that led us to this high value. Now you can see there's a slightly better one. Okay, so basically it's going to go through this process, and then it's going to it's going to save the best one as part of optimizer.max. So we just need to wait for this to finish its 20 iterations. And since there's 2 initial points, it'll usually end up being 22 or something like that. So that's pretty normal. Again, keep an eye on even if you are tempted just to like say, here's the best one and forget about the rest, just sort of keep an eye on the types of ranges, because if you can narrow things down, then the algorithm will converge just that much faster. For example, if you know that bagging is always something like 0. 0.9 or 1.6, then you might as well just start it at 0.9 or something like that. Similarly, with L2 learning reg, you can see that every time I've come up with the best value, it's been because it's been like 7 or 8. So I guess 0.02 may never give me an optimal value. So maybe I just start my range at 7 or 6. And maybe then I explore higher ones like 9 or 10. I had 10 as my limit, so maybe I'd do 12 or 15. You sort of just want to like kind of incrementally with trial and error sort of expand your thing. Again, you can never be entirely sure what the optimal value is, but the thing is, the wider the range, the longer it takes, and also there is always the chance that it doesn't converge. So you think that just having a wide range would be enough, that it would find things eventually, but sometimes like it would not only find things eventually, but it should in theory like end up with the same values as if you had a sort of smaller range but included that true mean or whatever. But just I found in practice that although you can sort of try to create a wide range, sit back and watch it do its thing, sometimes it's better to just narrow it down. Especially because you'll be running this over and over, right? Because you'll change your experiment, but there's no reason to sort of make the algorithm search over and over again when you already know generally what it should be. Like if I run this experiment again on this data set, I can see my n estimators is always 500. So maybe I should just make the search between 490 and 510 or something like that. Then it'll take less time. So now it's done, and you can sort of see the best ones are here, the best values, and you can sort of see the L2 here, the learning rate, max bin. But the problem with this is that if you want to use these as hyperparameters, then this max bin has to be an integer, this max depth has to be an integer value, and so does n estimators and num leaves. So what I do here is I would take all this stuff, which is basically it's two dictionaries, one of which has all these parameters in it. So I save it as best params, and then again I go through each column that is supposed to be an integer, and I take its value, which in this case, like for example 499.98, and I turn it into an integer, and then save it as f params, and that will basically now give me the same hyperparameters, except things like this will end up being integers. Then I'm going to use those parameters, f params, and then I'm going to fit this thing on the entire data set and then use the cross-validated score using the same splits to basically see how it does now when it's sort of trained on the entire data set. So yeah, you can see here that it comes out with a pretty good Matthews score of 94.7. And here you can see by the confusion matrix that it basically makes 3 sort of mistakes. I think actually you don't need to have this fit here. I think you can just do this, because the cross-val basically does the fitting as part of this. Part of this function is the fact that it fits it. I mean, that's the whole point of it, right? So there's no, you just have to define what the actual regressor is here. Oh, no, you need to fit it, I guess, because then it'll do that, so my bad. But anyway, let's take a look at this. So here's the SHAP values for this one. So this basically, you're using SHAP values to sort of understand the feature importance. And with SHAP values, you want to again fit the classifier on the whole thing. And just I mean, you did it above, but just just in case or whatever, you can just do it again. Now the explainer is a tree explainer. So this method, the dot tree explainer, or this function, is basically for tree-based algorithms like CatBoost and random forest and decision trees. So it explains this particular regressor, which is a tree. And I'm explaining the entire data set, and I want to know basically over the entire data set what the important features are. And here you'll see what they are. So you can see, I'll run this again. I feel like something is a little bit off here, but anyway, let's take a look. So we'll see here, just give it a sec. We'll see here that, according to this CatBoost model, polydipsia, polyuria are all very important features. That gender, itching, genital thrush, all this stuff is up here. Noticeably, age is kind of down here. You'll find that this, among other ones, tends, depending on the algorithm, tends to change like sort of rankings. Weakness and obesity tend to always be at the bottom, but stiffness usually sort of at the bottom. You'll see this in the next few videos, but partial paresis also can change a little bit, but it's really these two that don't change, and you can generally say that gender and age are usually kind of in the upper levels. That is, they're in the top 5 or 6, but it's hard to say exactly which is most important because each algorithm will sort of output a different thing. So here we have so far just the situation for the CatBoost.